Hello, assalamu alaikum. Today I am going to talk about, or to talk more about finding the inverse of an invertible matrix. Remember, we talked about invertible matrices before, especially if it is 2 by 2 matrix, and we said, well, here is the formula. You can use it to find whether a 2 by 2 matrix is invertible or not, and if it is invertible, here is the formula. You find the inverse. Now, the question is, in general, if we have a matrix in general, can we find whether it is invertible or not? And if it is invertible, can we find the inverse? Well, today we are going to talk about one method for doing that. And remember, for linear systems, we can write them in matrix form as AX equals B. So here you can think about motivation. If you have a linear system and you know that this matrix is invertible, then you can say here A inverse AX equals A inverse B, and A inverse times A, this is the identity. So here you get X equals A inverse B. So knowing the inverse of the coefficient matrix will help you to solve the linear system. Okay, so that is the reason knowing the inverse of your matrix is going to be helpful here. Okay, so the question is, how do we know whether the coefficient matrix or a matrix in general is invertible or not? And if it is invertible, how do we find the inverse? Let me here start by an example. So how to find A inverse. That is the question that we want to address. And here is an example. After the example, I explain the method and why it works. Consider A equals, okay, let me take this matrix. 1, 2, 0, 2, 1, 2, 0, 2, 1. This is a 3 by 3 matrix. We don't know whether it's invertible or not. And if it is invertible, we don't know what is the inverse. So how do we check that? Well, what you do, you write this matrix side by side. 1, 2, 0, 2, 1, 2, 0, 2, 1. And here the identity, 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay? We do elementary row operations here to reduce this matrix into a reduced row echelon form. We change it into a reduced row echelon form. Once you do that, you can decide whether it is invertible or not. And if it is invertible, what you get on this side is going to be A inverse. Okay? So the method here is fairly easy. What is the theory behind that? Why it works? I'll talk about it later on. But for the time being, let's see how to do it. Okay? So we want to do here elementary row operations and reduce this into reduced row echelon form. This is 1. We want here 0. So what do we do? Negative 2R1 plus R2. Well, let me do the first few steps. Then I'll let you finish that. So here is 1, 2, 0, 1, 0, 0. And here, negative 2R1 plus R2. That should replace R2. So we get here 0. We get here negative 3. We get here 2. Negative 2. Here 1. Here 0. And here we have 0, 2, 1, 0, 0, 1. The next step, we want this to be 1 and this 0. So I can write 1, 2, 0, 1, 1, 0, 0, and here negative 1/3 R2 should replace R2. So you get here 0, 1, negative 2/3, and here 2/3, and here negative 1/3, and here 0, here 0, 2, 1, 0, 0, 1. Now we want this 0, so 1, 2, 0, 1, 0, 0, 0, 1, negative 2/3, 2/3, negative 1/3, 0, and here negative 2 R2, add that to R3, you replace R3. So this will be 0, this will be 0, here 4/3, here negative 4/3, and here 2/3, and here 0. And next step, you make this 1, and then you can use the backward algorithm using Gauss-Jordan elimination, make this 0, and then you make this 0. So I'm going to skip here a couple of steps. I'll let you finish that. So here, keep going. You are going to get here 1, 0, 0, 0, 1, 0, 0, 0, 1. And here, you are going to get 3/7, 2/7, negative 4/7, 2/7, negative 1/7, 2/7, negative 4/7, 2/7, 3/7. And in this case, we say A inverse, hence A inverse equals 1/7. I can take this constant out, and here 3, 2, negative 4, 2, negative 1, 2, negative 4, 2, 3. Okay? This is the inverse of our matrix A. So getting that is just straightforward using elementary row operations. Okay? Now, here are two questions. Question number 1, how do we know if a matrix is not invertible? This one is invertible, and that's what we got. So what is going to happen if we have a matrix that is not invertible? Well, if it is not invertible, you will not be able to get the identity matrix here. Look here, this is the identity matrix. So if your matrix is invertible, the reduced row echelon form has to be the identity. If you cannot get that, what does it mean? It means you are going to get a row of zeros. So if you get a row of zeros, stop. Your matrix is not invertible. That's it. Okay? So basically, this method can help you to do two things. To check whether the matrix is invertible or not. And that you can see it once you reach the echelon form, or once you reach an echelon form. Okay? And if your matrix is not invertible, you stop. That's it. If your matrix is invertible, you keep going, get the reduced row echelon form, and here you get the identity, here you get a matrix. This matrix will be the inverse of your matrix. Okay? It works whether your matrix is a 3x3, or 4x4, or 100x100, or a million by million. It doesn't matter. Okay? So the method itself is easy. Of course, here you can expect, if your matrix is bigger, the numbers here are not nice. You can expect nasty computations. However, it is a very easy algorithm. I mean, we can use the computer to do that, and I'll show you how to do this using the computer in no time, okay? But for 3x3 matrices, 4x4 matrices with nice numbers, you should be able to do it by hand. It will be a few steps. So here, how many steps did I do? 1, 2, 3, 4, and here I skipped 3 more steps. So 7 steps will help you to find the inverse of your matrix. Okay, now the second question. Why does it work? 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 Why does it Why does it work like this? So we put the matrix here, we put the identity here, and we do elementary row operations, and we get what we got here. Well, why is that? Where is the logic behind that? Where is the theory behind that? Okay, this is what I'm going to explain now. And here I'm going to start by something called elementary matrices. Elementary matrices. A matrix E is called elementary matrix. If we can get it from a matrix A by an elementary row operation, by a single elementary row operation. Okay, so to address this question, we need to build some machinery here. We need to build some ideas, and then we address the question. The first thing here, we need to know what we mean by an elementary matrix. An elementary matrix is a matrix you get from the identity matrix. You get from the identity matrix, from the identity matrix by a single elementary row operation. So here is an example. E equals 1, 0, 0, negative 2, 1, 0, 0, 0, 1. This is an elementary matrix. Why? Because you can see, you get this from the identity. Here is the identity. 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 1. If you do negative to R1 and you add that to R2, you are going to get here negative 2. So this, you get it from this by, from the identity. Why don't I do it in 2 steps? So here it is, and once you do that, you are going to get negative 2R1 plus R2 will replace R2. So you get 1, 0, 0, negative 2, 1, 0, 0, 0. One single elementary row operation on the identity will give you this matrix. So this is an elementary matrix. What about this one? This is E1. What about this matrix? E equals 1, 0, 0. And here 2, 0, 0. And here 0, 3, 1. Is this an elementary matrix? Think about it. Is it an elementary matrix? No, it is not. Why? Not elementary. Why? Because to get this from this, you need 2 elementary row operations. One of them you multiply this row by 2, and one of them you multiply this row by 2, and you add it to this. So to get this, you need 2 elementary row operations, not 1. So here, single elementary row operation is crucial in our definition. Okay, it must be single elementary row operation. Okay, now after we understand the meaning of an elementary row operation, we come to this fact. Fact doing an elementary row operation on a matrix A is like multiplying A by an elementary matrix Think about it. When you have a matrix and you do an elementary row operation on that matrix, that will be exactly the same as if you multiply your matrix by an elementary matrix of certain form. Okay? Let me clarify this by an example. Let's take a whatever matrix. So let me take it 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? Now, do any elementary operation on this one, whatever it is. So let's say here negative 2R1 and add it to R3, or negative 3R1 add it to R3. So if we do that, we are going to get matrix A2 is 1, 2, 3, 4, 5, 6, and here I want to do negative 3R1, and I want to add that to R3, and I want to replace R3. So this is my elementary row operation. So this is going to give me this matrix, where here you have 4, and here you have negative 6 plus 8, 2, and negative 9 plus 9, 0. So this matrix is coming from this matrix by a single elementary row operation. Okay? Now, what we are saying here, this is exactly like if you take this matrix, A, and you multiply it 1, 2, 3, 4, 5, 6, 7, 8, 9. You multiply it by an elementary matrix. The elementary matrix, you get it from the identity by the same elementary row operation. So that will be 1, 0, 0, 0, 0, 1, and here negative 3, and this is 0, and this is 1. Double check, please. When you multiply this by this, what do you get? Can you do it? 1, 2, 3. Then this times this. Sorry, this is 1 here. The 1 is here. So this is 4, 5, 6. And here you have negative 3 plus 7, that is 4. Negative 6 plus 8, that is 2. This is 0. Here it is. Okay? So, doing this is like multiplying your matrix by an elementary matrix. So here, what are we saying? We are saying that each time you do an elementary row operation, here is your matrix, the matrix that you start with. Each time you do an elementary row operation, that is going to be like you multiply by an elementary matrix. Do another elementary row operation, you multiply by another elementary matrix. Do another elementary row operation, you multiply by another elementary matrix. Correct? According to this, each time you do an elementary row operation, it means you are multiplying by an elementary matrix. Okay? So in our method, when you start with A and you do elementary row operations, you are multiplying by those elementary matrices. And if that at the end gives you the identity, it means this times this is going to give you the identity. Okay? Now, that gives you a hint that this here is going to be the inverse of your matrix A. There is one more thing just we need to clarify here, which is fact number 2. Fact, elementary matrices are invertible. Elementary matrices are invertible. Why is that? Well, an elementary matrix is a matrix you get from the identity. So you do an elementary row operation on the identity, you get your elementary matrix. Now, let us think about reversing what you did. So here, what did we do? We multiplied R1 by -3, and we added that to R3. Correct? So we got this. Now, can we reverse this? What does it mean we reverse this? Well, instead of multiplying by -3, what do we do here? I want to reverse this back to this. If we multiply this by 3 and add it to this, look, 3 times row 1 added to row 3, this becomes 7, this becomes 6 plus 2, 8, this becomes 9. Correct? So if you want to reverse this step, what you need here is to multiply row 1 by 3 rather than -3 and add it to row 3. In that case, you go back to A. Okay? So each elementary row operation here can be reversed. Okay? And the reversal here will be multiplying your matrix by another matrix. So basically, you have E, you do a reversed step, you multiply it by E1, and in that case, you reverse it back to the identity. And if you have this, then it means this is the inverse of this. So this means E1 is E inverse. Okay? So clarifying this is fairly easy here. All you need is just to think about doing an elementary row operation and then reversing this back. Okay? So that makes each elementary matrix invertible. So once you recognize that, from here, you can multiply A, E0, E1, EK minus 1, and EK here, you multiply by EK inverse. This will be EK inverse. So this becomes the identity here. And keep doing this in the same way. You are going to get A equals EK inverse, EK minus 1 inverse, and at the end, E0 inverse. So using the properties that we discussed last time, this means A inverse equals, reverse this, what do you get? You get E0 inverse, EK minus 1 inverse, EK inverse, all of this inverse, and now it will be EK minus 1 up to E1, E0, and that is what we were expecting, okay? So The inverse of A is this. So that is the reason. That is the reason our method works fine, and it is not just a guess. Okay. All right. So the conclusion here: if you have a matrix and you want to know whether it is invertible or not, you use the algorithm we discussed. If you get a row of zeros, it means your matrix is non-invertible and you stop. If you don't get a row of zeros, you keep going till you get the reduced row echelon form. The reduced row echelon form will give you the identity on the left, and on the right, you get the inverse of your matrix. Okay, and here we justified that using elementary matrices and the relationship between elementary matrices and elementary row operations. Okay, so that's about finding the inverse of an invertible matrix and about elementary row operations and elementary matrices. Let me go back now to systems of equations. How do we use these ideas in solving systems? If you have a linear homogeneous system, so here it is homogeneous. Okay? Remember, homogeneous systems always have a trivial solution. Now, if your coefficient matrix is invertible, if A is invertible, then what? Then A inverse AX is going to be A inverse multiplied by the zero matrix, and that means X equals the zero matrix. So if your matrix is invertible, it means the trivial solution is a unique solution. Okay? So here, fact, if A is invertible in a homogeneous system, AX equals 0, then the trivial solution is the only solution. Remember, homogeneous solutions may have a unique solution or may have infinite number of solutions. Okay? So it is easy to discover whether the trivial solution is unique or not just by looking at the coefficient matrix and check whether it is invertible or not. Okay? If it is invertible, the trivial solution is the only solution. If it is not invertible, in that case, you are left with one option, which is you have infinite number of solutions. Otherwise, you have, so if A is invertible, you can say if A is not invertible, then this homogeneous system has infinitely many solutions. Okay? What if you want to talk about non-homogeneous systems? If you want to talk about non-homogeneous systems, and your coefficient matrix is invertible, A is invertible, you are going to get X equals A inverse B. So we have a unique solution. This means unique solution. So here the invertibility of the coefficient matrix will help you to figure out the scenarios that you have about solutions. Okay? A is invertible, it means you have a unique solution, and the unique solution, you get it like this. If A is not invertible here, then what happens? Well, in this case, you have two options. Either no solution or infinitely many solutions. Okay? So this is the relationship between invertibility and solutions of a linear system. Let me close this lecture by giving you an example of a linear system. consider the linear system. Consider the linear system x1 plus 3x2 plus x3 equals 4, 2x1 plus 2x3 plus 2x2 plus x3 equals negative 1, 2x1 plus 3x2 plus x3 equals 3. And here is my first question. Is the coefficient matrix invertible? If yes, find its inverse. To solve the system. All right, so how do we answer the first question? Well, so far we have only one method for answering the first question. So we write the coefficient matrix. Here it is. A equals 1, 3, 1, 2, 2, 1, 2, 3, 1. Then we write it side by side, the identity. Two, 2, 1, 0, 1, 0, 0, no, 2, 3, 1, 0, 0, 1. And we do elementary row operations here till we change this into a reduced row echelon form. I'm not going to write all the steps here, so please do it at home. Please do it. At the end, I'm going to give you what is the final answer. You are going to get 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 1. And here you are going to get negative 1, 0, 1, 0, negative 1, 1. And here 2, 3, negative 4. Double check that, please. So here, I'm skipping several steps that you need to do. Please do it using elementary row operations. So this is going to be the inverse of this. So your matrix is invertible because we are getting the identity here. And this is going to be the inverse of A. So here, hence, A inverse is negative 1, 0, 1, 0, negative 1, 1, 2, 3, negative 4. So we answered the first part of my question. Again, let me stress this. Elementary row operations, they are very simple, but you need to practice doing this fast, okay? So don't forget, you need here to do this at home. All right, let's go to the second part of the question. Solve the system. Well, in this case, the solution is going to be x equals A inverse B. So x is x1, x2, x3. A inverse is negative 1, 0, 1, 0, negative 1, 1, 2, 3, negative 4. And here is your B. B is 4, negative 1, 3. So all you need is just to multiply this by this. You get negative 4 plus 3, negative 1. Here you get 1 plus 3, 4. And here you get 8 minus 3. That is 5. 5 minus 12. That is negative 7. Again, 8 minus 3 is 5. 5 minus 12 is negative 7. So x1 is negative 1, x2 is 4, x3 is negative 7. That is our unique solution. Okay? So now you can ask yourself, if you have a question like this, would you do it using the method we discussed in the first section, or would you do it using the inverse of A? Well, obviously, if you have the inverse of A in front of you, then here it is very easy to do. Okay? That is sure. Okay? If you don't have the inverse of A in front of you, are you supposed to find it or not? If you are not asked to find it, in that case, you are free. You can just do it as we did in the first section. Okay? Otherwise, you need to find A inverse, and then you can use it as we did here and find the solution of your system. All right, so that's it here about finding the inverse of an invertible matrix, and after that, you can use it to figure out what happens to the solution of your system. Okay, so this is the relationship between the inverse of A and between the solution of your system. I have to stop here. So thank you guys. Please do your exercises and we'll see you next time.